Here in 6.7, we're going to look at Bayes' theorem, and here's a little information about Thomas Bayes. As you can see, he lived in the 1700s, so what we're going to do here is not exactly new. It's been around quite a while. So here's what Bayes' theorem does for us. It helps us revise the probability once we're given some new information. So suppose we already have an idea of how likely something is to happen, but then we get new information. So we would like to update our probability. That's what Bayes' theorem allows us to do. Here's an example. Suppose that in some population, 10% of the people use a particular drug. Now the test that's currently being used to detect that drug is 95% effective, which means that if you're using the drug, the test will detect that drug 95% of the time. 5% of the time, you can be taking the drug and the test will say, no, you're not. But then it goes on to say the test yields false positives 2% of the time. So that means 2% of the time you can not be taking the drug, but the test will say you are, right? A false positive. You get a positive result, but it's false. So you're not taking the drug, but the test says you are. Now, suppose some member of the population, randomly selected member, tests positive, takes the test, gets a positive result. What's the probability that person actually uses the drug? So at first, we're thinking, oh, this person tested positive. So, it's 95% effective. So we're thinking, oh, it tests positive. This person's probably using that drug. But let's see what Bayes' theorem has to say. So before we actually solve this problem, let's take a look at Bayes' theorem, Bayes' formula. And we're not just going to look at it, but we're going to derive it. Let's start with something we know. We know that the probability, this is a conditional probability, the probability that E occurs, given that F has occurred, is this fraction here. In the numerator, it's the probability of E and F. In the denominator, it's the probability that F has occurred. But we could also write the formula like this. Okay, instead of E given F, we could say F given E. That's going to be the same thing. It's going to be the probability of E intersect F. The order here doesn't matter. E intersect F, F intersect E doesn't matter. But now it's going to be by the probability divided by the probability of that last event, right? Probability of E. So those are two things that we know. Now over here on the right side, I'm going to multiply. I'm going to eliminate fractions. So I'm going to multiply both sides by the probability of E. So what I'm going to do is I'm going to multiply by the probability of E here. I'll multiply by the probability of E here. And you can see when we multiply on the right side that those P of E's are going to cancel. So that's going to give us that the probability of F given E times the probability of E is equal to the probability of E and F. Now, to make this just maybe make a little bit more sense, I'm going to switch the order of these. It doesn't matter which way I write them. So I'm going to write it like this now. The probability of E intersect F is the probability of F given E times the probability of E. Now look at our two formulas here. We have this one over here on the left and this one that we just developed. Now on the left, you see that numerator, probability of E intersect F? We just found a description for that. Probability of E intersect F is this expression right here. So what I'm going to do is I'm going to take this expression here, substitute it in place of this one. Right? So I'm going to take this and put it right here in place of that one. And that's going to give us that the probability of E given F is, okay, what have we got? The probability of F given E times the probability of E, all divided by the probability of F. There it is. This is Bayes' formula. Let's just take a look at what it says. So if we want the probability that E occurs, given that some event F has already occurred, here's what we're going to do. We're going to form a fraction, and in the numerator, we're going to reverse these, all right? We're looking for the probability of E given F. So we reverse them for probability of F given E times the probability of E itself, and then we divide the whole thing by the probability of F. So in the top reverse, multiply by the first probability of the first one, divide by the probability of the second one. So this expression here we call Bayes' theorem or Bayes' formula. And let's take a look now how to use that in this to solve this problem. And then we'll do some problems out of the text. So let's use Bayes' theorem to solve this problem. Let's just read it again. It's been a while. So suppose that 10% of some population uses a particular drug. Now, the test that is currently being used to detect the drug is 95% effective. That means that out of all the drug users, 95% of the time the test will detect the drug. 5% of the time it won't. And then it says the test yields a false positive. Now, positive means it gives a positive result for somebody who's not taking the drug 2% of the time. So for people who are not taking the drug, you go take the test and it'll say, yes, you are taking the test, but it'll say that 2% of the time. Now, so here's what you do. You take any member at the population. So take some random person in the population, give them the test, and they test positive. So what is the probability that the person actually uses the drug? So maybe it's not too intuitive here of what's going to happen, but a member tests positive. So what do you think? You test positive, you go away thinking probably using the drug. Let's see what Bayes' theorem tells us. So Bayes' theorem, I'm going to write like this. Here's what we want to know. We want to know, all right, what I'm looking for is this. What is the probability that a person actually uses the drug given that they test positive? All right, so I'm going to write it like this. What's the probability of actually using the drug given that you tested positive? That makes sense? So a member tests positive, so that's given, right? That's the given part. What's the probability that they use the drug? So I want to know what's the probability of using the drug given that you got a positive result. So here's what Bayes' theorem is in terms of these symbols. So we know on the numerator you reverse, so it's the probability of positive given the drug times the probability of the first, which is the drug. Right? So I reverse them, D given positive, I reverse getting positive given D, and then multiply it by the probability of the first one. And then you divide by the probability of the second one, probability of a positive result. So let's look at this and see what we need, right? Look at our formula, see what we need. We need probability of, okay, what are these? Probability of the drug. Well, here's what we have. 10% of the population uses the drug. So I do know this one. The probability of using the drug is 10%. Now, what about this one here? This is the probability of a positive result given use of the drug. Well, what this says up here, it says the test currently used is 95% effective, which means if you're taking the drug, you get a positive result 95% of the time. That's this. Probability of a positive result given use of the drug, that's 0.95. So we know that one. Probability of a positive given drug use, that's 0.95. Now, we also need this, probability of a positive result. We have to be a little bit careful here because we could get a positive result two ways. First of all, we could be taking the drug, get a positive result, or we could not be taking the drug and get a positive result. Here's, I think, a nice way to get the denominators in all of these types of problems. I'm going to use a tree diagram. So down here, I'm going to start with a tree. Now, I'm going to start it this way. What happens? Well, you start out with two branches. You can be using the drug or not using the drug. Then you take a test. So the test can give you, say, a positive result or a negative result. If you're not taking the drug, you still take the test, you get a positive result or a negative result. Now, what's the probability of taking the drug? Well, the problem tells us that 10% of the population takes the drug. So this is 0.10, so 90% must not take the drug. And now, up here on this branch, if you're taking the drug, what's the probability of a positive result? Okay, well, if you're taking the drug, the positive result, that's going to be the 0.95. Now, what about down here on this branch? If you're not taking the drug, what's the probability of getting a positive result? Well, that's up here, right? It says the test yields false positives in 2% of the test. So false positive means you get a positive, but it's false. You're not taking the drug, but it came out positive. That's down here. You're not taking the drug, but it comes out as a positive test. That's 0.02. So they have to add up to 1. So it must be 98% of the time, if you're not taking the drug, you get a negative result. Now what we're looking for is this denominator. That's getting a positive result. Well, look down here. How do you get a positive result? You could get it right here, right? You could get it right here, or you could get it right here, right? You could get the top one or this one. Now, to get the top one, we're going to be here. This is going to be 0.10 times 0.95. The or is a plus. Or you could be down here. And how do you get to that plus? You have to go down here and here. So it's a 0.90 times 0.02. So it's the 0.90 times the 0.02. All right, so we're close. Let's plug our numbers in. So what's the probability of taking the drug given that you got a positive result? All right, kind of a big fraction bar here. So in the numerator we already have this number here, right? Positive given the drug. That's the 0.95. And the probability of the drug, that's the 0.10, right? We have those numbers there. So this is going to be 0.95 times 0.10. Now the denominator, we just went through a bit to get that, right? The denominator is a positive, and here's how we get a positive. So I'm going to add those together. So we are going to get 0.10 times 0.95 plus 0.90 times 0.02. So when I carefully did that on my calculator, I got this. I got I'm going to round to 4 decimal places. I got 8407. 8407. Now, if I convert that to a percent, right, this is going to be, if I convert it to a percent, it's about 84%. So here's what this is telling us. 10% of the population uses a drug, and the test is about 95% effective in detecting the drug in drug users. So a randomly selected person from the population goes into the lab, gets a test, comes out positive. So what are we just thinking? We're thinking that this person's probably taken the drug. But what's the percentage, what probability is that person really taking the drug? There's really only an 84% chance that that person is taking the drug. Now, I want to mention something here before we just stop here, is that back in our tree diagram, how did I know what to do first? I did drug, not drug, and then positive, negative. If I had tried to do this, what if I did this way? This will always be a question that you come up with. Okay, so what's the probability of a positive? See, if I try it this way, I don't even know what to put here. There's no numbers. What's the probability of a positive result? Well, the probability of a positive result depends on if you're taking the drug or not. And anyway, in the sequence of events, what do you do first? You're either taking the drug or you're not taking the drug. Then you go take the test. It's not that you do this. You get a positive result, then you take the drug or not take the drug. So just think about it in terms of sequences. Which event would you do first? And make that the start of your tree.